I used to do apartment maintenance in Minnesota, and I encountered a lot of incinerators in old apartment buildings. While my newer multifamily buildings have a metallic spiral trash chute that allows you to drop trash into dumpsters on the ground floor, my older buildings lacked a trash chute but had these ornate cast iron steel hatches that allowed tenants to drop trash into a cinder block chute with a masonry firebox on the lowest level. Every hatch that I've encountered has been bolted shut, likely by the building management as a condition of getting their certificate of occupancy, which is a document issued by a municipality during the sale of a multifamily building. The incinerators were likely constructed after the introduction of concrete masonry units to Minnesota in the 1940s and closed in the 1970s and 80s. As originally constructed, these incinerators were an environmental and public health disaster. The EPA was established in 1970, and one of its primary missions was to reduce urban smog. While EPA requirements for motor vehicle emissions and fuel economy can be fairly visible to consumers, it regulates stationary sources of pollutants through an often invisible process of licensing and permitting. The Clean Air Act, originally passed in 1963, has expanded to define many different categories of stationary emission source. These include combustion appliances like furnaces and standby generators, power generation plants, industrial processes, municipal-scale waste incinerators, medical waste incinerators, and small wood or waste-burning appliances like wood stoves, outdoor boilers, and residential incinerators. In order to receive or maintain a permit for the construction or operation of these stationary sources, producers or operators have been required to demonstrate allowable levels of various emissions, including carbon dioxide, carbon monoxide, sulfur and nitrogen oxides, lead, ash, particulate matter, ozone, mercury, and dioxins. The high cost of controlling these emissions have made apartment incinerators practically illegal for many decades, although local permitting authorities have allowed some older units to continue operating in cities like Chicago or New York to this day. Controlling the emissions in a waste incinerator is typically more difficult than in a wood or coal burner, because residential waste is typically wetter, contains many non-combustible components, and contains various plastics with different combustion properties. In order to completely reduce the carcinogenic oxides and dioxins produced from the combustion of organics and plastics, complete combustion is required. Mobile combustion sources usually achieve complete combustion using a catalytic converter and electronic fuel injection, while stationary sources use a combination of things, including a preheating of fuel air, recycling of combustion gases through the combustion chamber, and a large amount of insulation of the flue and combustion chamber to increase the temperature up to the 1200 degrees Fahrenheit required to completely reduce dioxins to their inert components. Ash and particulate emissions are typically captured in coal plants using scrubbers, electrostatic separators, and baghouses, but are often ignored by wood stove manufacturers and other small-scale emission sources that fall under more lenient EPA classes that are assumed to operate infrequently. The permitting of scrubbers can be difficult as they capture pollutants in a spray of water and generate wastewater that is acidic and can contain heavy metals and mercury. When installed on combustion sources other than coal, the wastewater won't be expected to contain heavy metals but would still be acidic. To my knowledge, baghouses and electrostatic separators aren't used outside the coal industry to control emission sources, Although electrostatic air filters are used in some central air systems and baghouses are common in industrial dust collection systems. They aren't particularly expensive, high maintenance, or difficult to miniaturize. Municipal scale waste incinerators have been operating for as long as we've had cities. Modern emission standards shut down many of the older facilities in wealthy nations, but new technologies and techniques have allowed the practice to persist. The development of plasma gasification, continuous process automation, and economies of scale have enabled municipal incinerators in Japan, the Netherlands, and the United States to not only meet strict emission standards, but also generate electricity or heated water to warm up nearby buildings. In the United States, though, incineration is neither as cheap a method of waste disposal as landfills, nor as cheap a method of power generation as natural gas, while generating more carbon per kilowatt than coal. I'm still attracted to the idea of local incineration for its potential to reduce the methane emissions and habitat impacts of landfills, reduce the need for transportation of our trash, and reduce energy dependence on coal and natural gas. The high-rises of the future may be built with incinerators that can generate combined heat and energy while complying with future emissions regulations. Developing nations without robust trash collection systems or emission standards have been pioneering a variety of small, mobile, and packaged incinerators, and their waste infrastructure could potentially develop in a completely different direction than ours. Alibaba sells incinerators both in these less regulated markets and provides medical or biowaste incinerators to more regulated markets. Incinerators for medical waste or cremation occupy their own category within the Clean Air Act, with slightly looser standards than other stationary emission sources, as they are not assumed to operate continuously. They are also designed with different priorities than other incinerators, and tend to have relatively low levels of automation and consume large amounts of electricity and natural gas in order to evaporate all the water in their feedstock. Medical incinerators in the United States are typically bought and installed much like smaller packaged combustion appliances. Historic masonry heaters may offer better inspiration for high-rise waste incinerators than modern combustion appliances. British wash coppers, Russian stoves, Korean angungi, or the rocket stoves built by many American survivalist communities have been able to achieve extremely high internal temperatures and extremely low emissions through the sophisticated management of thermal mass and airflow. The abundance of wood and late urbanization of colonial America stifled the development of a masonry heater industry to the same degree of sophistication as we see in the Old World. The old incinerators in my Minnesota apartments were just a cinder block chute with a slight widening at the bottom. Many municipalities in the U.S. had to introduce building codes that required trash chutes to be separate from the flue to prevent a trash clog from flooding the building with carbon monoxide. An upscaled old-world masonry heater should be able to function as a code-compliant high-rise incinerator with some modern additions like the catalytic electrostatic or media filtration of flue gases. They could also be mostly prefabricated from precast concrete, reducing cost and build time. The biggest hurdle may be the maintenance of the 1200 degrees Fahrenheit required for complete combustion. On startup or shutdown, insufficient temperatures create a lot of carcinogenic smoke, as many of us have experienced with grills or wood stoves. Large-scale municipal incinerators have an abundance of feedstock and can employ people around the clock to keep the equipment fed and hot 24/7. I think that these continuous temperatures may be feasible on a smaller scale by building a small, well-insulated burn chambers, a shredder operated by a light curtain, and a pellet stove-inspired hopper operated by a thermometer. Such a system could operate itself continuously if your tenants can be trusted to only throw away relatively dry combustibles. If not, maybe humanity is not meant to survive. Similar compactor systems operate in many high-rises and department stores today, but they have some reliability issues. Many discount light cartons are easily misaligned by falling trash, and thermometers are subject to a lot of thermal stress. And tenants are always trying to fit larger objects into the chute. But if quality components are used and the chute is sufficiently larger than the chute doors, a self-feeding incinerator is possible with existing technologies. It would consume a similar amount of electricity to compactor systems with slightly greater mechanical complexity. Heating up domestic hot water or hydronic heating fluid with an incinerator would not require huge modifications to existing systems or practices. Large buildings already require circulation pumps in order to maintain the temperature of hot water pipes. Rerouting these pipes through an incinerator may offer significant energy savings. The main barrier is the high operating temperature required for complete combustion in incinerators. This could potentially overheat and vaporize water, causing bricks and water tanks to explode. An excess of heat could require the system to vent significant amounts of water into the sewer. Certain states place hydronic heating boilers into different regulatory categories based on their BTU output, and higher levels of education and experience and certificates are required to regularly inspect and maintain boilers with greater output. A high BTU rating could significantly increase the labor costs of operating incinerators by requiring more qualified professionals to do daily or weekly checks on the operating temperatures and pressures. In Minnesota, these rules are often skirted in large buildings by using many small boilers in series in order to serve large loads. This makes installation and maintenance easier and allows the checks to be performed by the least certified of boiler professionals. A particularly lenient rural permitting authority may treat an incinerator as an exterior wood boiler, which is a fairly mundane combustion appliance. But an incinerator could offer significant energy savings simply by circulating heated air around lower levels and lobbies and underground garages without being tied into a hydronic heating system or domestic water system. During summer months, a variably louvered chase around the incinerator units could vent air from underground garages up around the flue stack and provide cooling, ventilation, and a route for fire to escape through the roof without spreading through the building. A hotel staircase that I encountered in Appleton, Wisconsin had a large louvered hatch in the ceiling that was likely tied into a fire alarm system, but may also have been opened on hot days. The inherent danger of pressure vessels and the high cost of regulatory compliance may make small steam power generators economically impractical. The thermoelectric effect is used to generate small amounts of electricity in water heaters and some sensors. I'm not sure why this effect isn't used in larger generation applications, but I suspect that it has something to do with the low yield and high cost of the materials used. The most practical method of generating electricity from a small incinerator may involve a steam cycle using a relatively low-pressure refrigerant, but I'm not optimistic that small to medium-sized incinerators can economically and legally generate electricity in our current technological and regulatory environment. But I believe that we do have the technology to economically and legally generate heat in small and medium-sized incinerators, given a sufficiently liberal permitting authority, and to divert a lot of trash from landfills and trucks from the road.